Take your time. Here's the practice final I wrote. I will post some solutions to it eventually. Let's see, what else was I gonna do here? I mean, yes, it's certainly it's based more off of an exam that Lee wrote, but it is viable for both instructors. And there's extras, you can just put them on one of the tables over there. All right, I guess we should get started. So a couple things before we get started. Just as an FYI, let's look at Canvas for a second here. Where'd you go? Where's that thing? There we go. Okay. Just wanted to point out a couple things in Canvas, just so you're all aware of them. I think I mentioned this last time. In case I didn't, there's a survey to take for the course or an evaluation of me. Please fill it out when you have a second. It takes maybe 5 minutes. It is anonymous, so whatever you say, good or bad, will be. I won't be like, oh, I can't believe they said that. No, just be like, I'll get the feedback from my supervisor, and it'll be great. What else? There was something else to mention. Oh yeah, if you scroll down here a bit, quite a bit, to the exam prep material, you'll see the practice final that I just handed out to everybody. You'll see the solutions eventually once I post them, right? They're there. I just haven't made them available yet because I'd like to give you the chance to work on the final practice final without the temptation of looking at the solutions. So definitely try to do it on your own without looking at the solutions. I'll probably post them. When's your guys' final? Wednesday? Okay, so I'll definitely post them by like Saturday at the latest. Today is what? Wednesday? Yeah, Saturday seems reasonable. In fact, I could probably do that right now. And then I will also point out there's a few other things. There's a couple reviews on there with solutions. Those are worth looking at. I would say if you're looking at a review and the problem seems like something you haven't ever covered in class, you should just skip it, right? Don't do problems on the review that seem like they aren't things you have learned or talked about in class at all. I think that's all I had to say about that. Any questions about any of that? I think I made barely just enough copies of the practice final, so hopefully everyone got one. And who are you? Okay. What else? I feel like there was another thing on my mind. Maybe I forgot. I might as well throw around the attendance form while I'm thinking of it. Yeah.
Scroll down on old practice.
This is an old 17C practice. I mean, I can certainly make that available as well. I don't remember what it looks like, but sure. There's an older 17C final. There's the solutions, and there's a video of me going over the solutions. Yeah, that's probably useful. I mean, it can't hurt. I will look at it later then and see if there's any problems that I think are really kind of not relevant. So that begs the question then, what's on your mind today? I know some of you still have a homework assignment due today, right? Are there any bothersome questions in that homework assignment yeah, sure. Sure. And I had the homework assignment up and then I lost it. Oops. Oh, what did I just do? I think I just pressed a weird button though. Sorry. Yes, I did press a weird button. Let's see if I can fix it. No, that's not better. That's not better. That's not better. You know what you should do? That looks normalish, I think. I mean, sure. We'll buy that. I know I did have it. So sure. Yeah. A couple things to talk about. Sure. So that. Oh, that's it. I think the homework assignment for Varn for this due today printed out. So if you know which question number you're looking at, I have it right here in front of me.
Is number 10.
Well, with Paul and Cindy?
Yeah.
Okay. Yeah, I think someone else asked me this question before, and it's kind of a tricky question. So I would say most of these like counting questions are kind of tricky for lack of a better term. Like they're just, there's always something special to consider. You kind of have to think about what is happening. So let's look at, let's write down, so this is Co-17C. It's the last day of class, June 4th, 2025. And here's question number 10. So here's my setup. Paul and Cindy and 10 of their friends, a lot of friends, and we're going to have dinner at a round table with 12 chairs. So sit at a round table with 12 chairs because there's 12 of them. Where'd it go? Sorry, I lost it. The chairs are labeled, and this is an important piece of information. The chairs are labeled 1 through 12. And then the question is, in how many ways can the people sit in the seats? In how many ways can all 12 of them choose seats? They even helped you out by using the word 12 there, or by using the word choose, 12 of them choose. Although I don't think it's that helpful actually. Seats. If Cindy sits to the left of Paula, or Paula. Okay. I often find for questions like this, it's useful to draw a little picture. So I've got my 12 seats. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And then I usually start asking questions like, how many can Paula pick a seat, or how many choices does Paula have? Paula, right? Yeah. So how many choices of a seat? If Paula sits down first, how many seats does she have to choose from? 12. So the first person who sits, Paula, there's 12 choices. Okay. So let's say Paula sat here. How many choices does Cindy have? Right, like you could say one or none, right? She has to choose to sit in a seat. You could say that's one choice, or really she has no choice, meaning the seat she is sitting in is predetermined. She must sit to the left of Paula, so she's got to sit right there. So Paula's choice is also making Cindy's choice for her. So that's not going to change the number of ways we can do this, right? There's still only 12 ways Paula and Cindy can sit down. Paula can sit here and then Cindy is there, or Paula sits there and Cindy is there, right? There's only 12 choices. And then the next person, well, there's 10 seats left to choose from. So there's 10 choices, and then 9 for the next person, and 8 for the next person, and 7, and 6, and 5, and 4. So we've got 12 times 10 factorial. So the number of ways Paula can pick a seat, and then the number of ways the other 10 people can choose the seats they're going to pick from. And I know I'm saying the word choose here, but it's not like the choose, it's really more of a permutation situation, right? We're talking about all the different ways, possibilities of how the people can sit down. Now, this question is different if you don't number the chairs. So what if the chairs aren't numbered? I know that's not a question in the homework, but I think it's worth asking. Well, then really, and it's kind of sound kind of weird. Paula doesn't really have a choice, or really any choice is the same choice at a round table. Because wherever someone sits at a round table, you can say, well, if they're not numbering the chairs, I'm going to picture that as being the head of the table. So Paula is always seated at the head, and then Cindy is always to her left, and then the other 10 people have 10 factorial ways of sitting down. So if the chairs weren't numbered, there's only 10 factorial ways of sitting the people, because essentially, I'm going to try and make it like if Paula sat here and what's her friend's name? Cindy sat here, and then let's say persons, 1 through 10 sat here. If everyone moves one seat to the left and the seats are numbered, that's a different seating arrangement because people are sitting in different numbered seats. But if everyone moves one to the left and the seats aren't numbered, as far as an outside observer is concerned, it still looks the same as it did before. The seating arrangement is still the same. Each person has the same person to the right, same person to their left. And that means there's only 10 factorial ways of doing that if we don't number the chairs. Kind of a weird facet of this problem, but it is true. Or not this problem, but like similar problems. I see some of you thinking like, really? Yes, really and truly, but it's kind of bizarre. Questions about that? Um, yeah.
I feel like communication and publication is set that has to be creating family less.
No, I really like I would almost never use the permutation formula at all. Like it's not a good formula to use. It's better. Like I'm technically, am I using it here? No, I don't know. I don't really think about it that way. That way I know it's not helpful. Um, but no, I would not particularly specifically the permutation formula. I don't think that's one you should think about using really. You should just be like, okay, well, if in a very typical example, if I'm picking, four people to form a committee out of a group of, say, nine people, how many ways can we do that? Well, since I don't care what order I pick the people in, right? It doesn't matter if I pick me first then you or you first then me. It's a choose one. Then this is where I would use a formula. I'd say, okay, that's going to be nine choose four. It's probably fine to leave it like that, but if you feel like you have to write it out a little bit, you could say it's 9 factorial over 4 factorial times 5 factorial. I don't think you should simplify this any further, really. You can if you want to. It does get simpler, but not a lot. On the other hand, if I asked the same question, but then said in that group of four people, I'm going to choose different titles for them, like a president, a vice president, a treasurer, and I don't know, a secretary, sure. Then the order I assign them in, or the order I picked, like I can imagine, I'm picking the first choice to be the president, the second to be the VP, the third to be the treasurer, and the fourth to be the secretary. Then the order does matter. And so I'm still not going to use that permutation formula. I don't like it. I don't remember it, to be honest. I know that, cool, I have four slots, president, VP, treasurer, secretary, and of the nine people, how many choices are there for the president? Nine. Cool, I picked the person. How many are left for the VP? Times seven, times six. That is way easier to do, I think, than remember that my, nine, my permutations of four people out of nine people, however you write that formula, which I do not love this notation, is 9 factorial over 9 minus 4 factorial. That is not easier to remember for me. Maybe it is for you. Maybe you love this formula. It's great. It's fine. But I just like to think about kind of how many slots and how I can fill those slots. Yeah. Wait. Before we move on, is there more about this before we move on? I feel like I had something else to say about this. I did kind of, but we can come back to it later. Okay, go ahead.
Needed for boy and girl.
Let's see, 20. Okay, yeah, let's see. Color blindness is an X-linked inherited disease. A woman who carries the color blindness gene on one of her X chromosomes, but not on the other, has normal vision. A man who carries the gene on only his X chromosome is colorblind because he doesn't have another X chromosome to make up for it. A woman with normal vision who carries the color blindness gene on one of her X chromosomes has a child with a man who has normal vision. What is the probability that the child will be colorblind? And so obviously this question requires some knowledge about like how gene things work. You have a dominant, recessive, you can get what like so the thing that's kind of interesting here or problematic is we know some stuff, but we don't know everything. So let's write down what's important. This is number 20. I mean, what's important might vary by what you think. But let's see, we have a woman with normal vision. So the woman could have, I guess we have to label things here. I have to pick names for things. So she could have like, she could either have an X chromosome with not being colorblind and an X chromosome with not being colorblind, or she could have an X chromosome with not and an X chromosome with being colorblind, right? We don't know what her both of her chromosomes are. We know she's not colorblind in both of them because then she'd be colorblind and she has normal vision. And then she has a baby with a man who has. Oh wait, I apologize. I misread the question. Let's read it again. If a woman with normal vision who carries the color blindness gene, well, that's out. on one of her X chromosomes has a child, right? Because if she didn't carry the colorblindness gene, right, then we would know that the kid couldn't be colorblind because it would have a normal X chromosome and whatever Y chromosome or whatever X or Y chromosome the husband, the partner, the father gave her. Um, so, so there's the woman, and then the man has, what's the man have? The man has normal vision. So that means he has to have an X with a normal and whatever the Y thing is doing. All right. So really it's just like four combinations. So we've got the man can either donate this one or this one. The woman can donate this one or this one. I wish they'd given us like nice labels here. So we're either going to get this XNXN, XNY, XNXC, XCY. So we now have to pay attention to the question. The question asks, what's the probability that the child will be colorblind? How many of those four combinations produce a child that is colorblind? Just one of them. The one where we have a boy with a colorblindness gene. This one over here, where there's a colorblindness gene, and another non-colorblindness one is going to produce a girl much like the mother, with one normal and one colorblind, or whatever, non-colorblind. So yeah, it looks like there's a 1 in 4 chance. One way of getting what we're asked about out of four possible ways of anything happening. Reminds me, so in case you are as bad at biology as I am, which is probably not the case, but you never know. Some of you might not be bio majors, although in this math class, many of you are somewhere in the biology world. But there is a handout here. Where'd it go? Where is it? It was somewhere in here. I thought I posted it. Sorry, apologies for not knowing where stuff is. Oh, it's all the way down here. This terminology for probability handout. If you look at that, it says stuff about cards and poker hands on the second page, but it has stuff about genes and stuff on the first page if you need a refresher on that. So there's a nice handout here. If you do need to know about how cards and poker works, it's all right there in nice color. So yeah. Yes. Yes.
Yeah. And for
Right. And I made it up. I just picked my own notation. But it would have been probably a good idea for me to have written that down. So I could have said XN is an X chromosome that is not colorblind, and XC is colorblind.
question say that the male was colorblind.
No, I believe it said not. So, but maybe I'm wrong. I could be. This is a really good lesson in making sure you read the question carefully. Colorblindness is an X-linked inherited disease. A woman who carries the colorblindness gene on one of her X chromosomes, but not on the other, has normal vision. A man who carries the gene on only his X chromosome is colorblind. But that's just telling us how it works. So if we read the next part, a woman with normal vision carries the colorblindness gene on one of her X chromosomes, has a child with a man who has normal vision. So yeah, so I did read it correctly, but yes. Does that make sense? So here's my man with normal vision. He's got to have a non-colorblind X, and the Y doesn't matter. And here's our woman who are specifically told has one normal and one colorblind. Here's a better question. What if they just told you the woman had normal vision? Interesting. So if on the other hand, we know that the woman has normal vision, well, then she could either be this genotype or this genotype. And making some assumptions about how often this occurs, I'm going to assume each one is equally likely. There's a 50% chance she's this, but that's probably not a fair assumption, but okay. And then the man is still this. So now the question is, what is the probability their child will be colorblind? This is a great opportunity to use a tree. So first, let's talk about the gene the woman donates. Well, first let's talk about the woman's genotype. So there's a 50% probability that she is XNXC, and there's a 50% probability that she is XNXN. And really, we don't have to travel down this path anymore because if the woman has XNXN, there's no way the child's going to be colorblind because it's definitely going to have an XN chromosome. If it's a Y, then it's normal. And if it's another X, then it's whatever. Well, and the man's also right. So then the man could either, right. So then she could either donate XN or XN 50% of the time. And then the man could donate either an XN or a Y, or an XN or a Y, both 50%. Sorry, my writing is less than good here. So each of these four of the possible total 8 outcomes are equally likely at this juncture. So now let's look at the other way this could go. You could have the woman donating a normal or non-colorblind and a colorblind. And then the same sort of things here. The man could donate normal or Y, and here the man could donate a normal or a Y. Each of these with the same 50% probability each time. So, of all these paths, there's only one way you get a colorblind kid. This path right here, where the woman happened to have had one colorblind gene to start off with. We don't know, but that could have been the case. And then she donates her colorblind gene, and then the man donates a Y so that they have a colorblind boy. So this first branch is selecting, the genotype of the woman. The next branch is which gene she donates. The next branch is which gene the man donates. Yeah. Okay. So out of these 1, 2, 3, 4, 5, 6, 7, 8 possibilities, 1 out of 8 of them is going to be a colorblind kid. So if we don't know the genotype of the mother, but we know she is not colorblind, then we do know that the father is not colorblind. There's a 1 in 8 chance of having a colorblind kid, assuming equal likelihood of either thing. I would also point out you could multiply all these probabilities together. 0.5 times 0.5 times 0.5 is 1/2 times 1/2 times 1/2, which is 1/8. Okay. Other questions? Actually, pause on your other questions because I do want to give you one more example before we are done with our time together. So where'd you go here? Apologies. Is this the one I want? I definitely want to make sure you see one more Bayes rule example for sure. Sorry, it's not it. Nope, that's not it. Might just make one up, but sorry, my notes are all over the place. Yeah, here we go. So here's an example. And again, there's a number of ways to approach this, but I'm going to show you what I think is the best way. A rare disease affects 1 out of 1,000 people. A blood test correctly detects the disease 99% of the time. But also gives a positive result in 2% of the cases when the person does not have the disease. Also known as a what? Thank you. And I'm just going to jump to so there's kind of an intermediate question we often ask here. I'm going to jump to the point, which is what is the probability that a person who tests positive has the disease? There's a few different ways you can label things here. Often, it looks terrible. Sorry. Often for these ones, I like to pick D as having the disease. So I often write it this way. D equals you have the disease. D complement is you do not. And then for testing positive or testing negative, we often use a plus or a minus sign. Although that's not, or you could use like another letter. You could say like P is testing positive and P complement is testing negative. Either way is fine. So you can say plus is you test positive, minus is you test negative. And I saw a hand over there.
This might be a dumb question, but like the, the test detects 99%, but gives a result of 2%.
So here's what this says. A blood test correctly detects the disease 99% of the time, meaning if a person has the disease, you will get a positive test result 99% of the time. So if you tested 100 people that had the disease, 99 of them would come up positive and one of them would come up negative. And then, the reason I've written it this way, well, the reason it's written this way is so this is how it's usually phrased in questions. They tell you it does this 99% of the time, and also it gives a positive result in 2% of the cases when the person does not have the disease. So if the person doesn't have the disease, then the probability of testing positive is 2%. Those are both conditional probabilities. They're just written very, very wordily. So what those both mean is we know that the probability of testing positive, given that you have the disease, is 99%. The probability of testing negative, given that you have the disease, is two. Oh, nope, that's not the right thing. I was about to say the wrong thing here. What I really wanted to say here is the probability of testing positive, given that you do not have the disease, is 2%. Although we can certainly figure out what this is. If you have the disease, you either have to test positive or test negative. So if you have the disease and there's a 99% chance of testing positive, there is a 1% chance of testing negative. And similarly, you all should write down and not say any words and write down what the probability of testing negative given that you do not have the disease is. Okay, so that's going to be 98%, 0.98. So there's a number of ways of answering this question. They're asking us, what is the probability the person who test positive has the disease? So in other words, what's the probability of having the disease given a positive test? That is the question that's on deck. And even though I want to use a tree, I would point out, I would almost always do one thing. If I'm ever trying to find a conditional probability, I'm always going to rewrite it as the quotient. So this probability of having the disease given that you had a positive test is equal to the probability of having the disease and having a positive test divided by the probability of testing positive. We're going to do this without a tree first, just to see how you can get there. So let's fix the bottom. The probability of testing positive, well, you can either test positive and have the disease or test positive and not have the disease. That's called the law of total probability. If you're trying to find the probability of something happening, it's the probability of that thing happening intersected with all the other things that can be true that are not the complement of that thing. So you can either have the disease and test positive or not have the disease and test positive. And the top is still this. Okay. And the next part of this part is the part where I kind of fall apart, where I don't like the formula so much. But we want to find this conditional probability, and we have the opposite conditional probability. We know the probability of testing positive given you have the disease. So the probability of having the disease and testing positive, this top part is equal to the probability of, let me make sure I say it right, having the disease multiplied by the probability of testing positive given that you have the disease. On the bottom, that's actually the same, right? This part here is the same as that part there. So that's going to be the same thing right there. Plus, this is probably that's a bad choice to use the positive signs here because the positive sign could really get mixed up with the plus sign there. So maybe not the best choice on my part. Over here, the probability of not having the disease and testing positive is the probability of not having the disease multiplied by the conditional probability that we test positive given that we don't have the disease. And now, looking at our conditional probabilities up here, we know all these pieces except for one. Well, we haven't written it down, I should say. The only thing that's in here that isn't already there, I have the probability of testing positive given the disease. I have that again. I have the probability of testing positive given that I don't have the disease, but I don't have the probability of having the disease. But they did say what it was in the problem. A rare disease affects 1 out of 1,000 people. So the probability of having the disease is 1 out of 1,000, or if you prefer a decimal, 0.001. And the probability of not having the disease is, well, the complement probability is always 1 minus the other one. It's going to be 1 minus 1 over 1,000, which is 999 over 1,000, or if you prefer, 0.999. Now we have all the pieces we need to write down what this is going to equal. So it's going to be P of D, which we just said was 0.001, times P of the probability of testing positive given you have the disease, which is 0.99, divided by this, literally the same thing goes right there. 0.001 times 0.99 plus now the probability of not having the disease, which is 0.999, multiplied by the probability of testing positive given you, that you don't have the disease, which is 0.02. Which is approximately 0.047 or 4.7%. And that's fine. And you can memorize that formula if you're good at memorizing things. I've probably memorized it at this point just because I've said it so many times in my life, but only really that. I definitely didn't memorize it when I was a student. I memorized this. You can draw this sort of diagram. It says, well, on this tree, on the first branch, you can either have the disease, there's a 1 in 1,000 chance or 0.001 probability, or not have the disease, 0.999 probability. And then on this first branch, given that you have the disease, you can either test positive or test negative. The probability of testing positive given that you have the disease is something we were told. It's 0.99. The probability of testing negative given that you have the disease, well, it has to be whatever's left over from 0.99, which is 0.01. Similarly, the probability of testing positive given that you don't have the disease, we were told was 0.02. And that means the probability of testing negative given that you don't have the disease is 0.98. Now, technically, what I should be writing here is this, right? This is the probability of testing positive given that you have the disease. This is the probability of testing negative given that you have the disease. This is the probability of testing positive given that you don't have the disease. This is the probability of testing negative given that you don't have the disease. But we really don't need to write those things because the tree tells you that. You're finding the probability of being positive given that having the disease has already happened. You're on the branch where you have the disease. And then if you want to calculate the same thing without doing all of the writing of formulas, you can do this. The probability of having the disease given that we tested positive. Well, I still use the first version of the formula. It's always the probability of the intersection divided by the probability of which thing? The D or the plus? I mean, I know it's literally on there somewhere, but always the thing that's given, always the second thing right there. And then I'm just going to look at my tree. Ooh. So the probability of having the disease and testing positive means we need to follow the branch or the path that has those two things on it. So it's going to be having the disease multiplied by testing positive because we want to have the disease and then test positive. So it's 0.001 times 0.99 divided by the probability of testing positive. That's going to be all of the pathways that get us to a positive and test result. So it's this pathway here, 0.001 times 0.99, or plus this pathway here, having not had the disease and testing positive. So 0.999 and times 0.02. I think it's easier to see it this way. But again, I'm not you, right? You might think it's easier to do it the other way. So do whatever works for you. But definitely, if this works for you, I think you should do it. It's totally valid to do it this way. I think it's very convenient. All right, that's what I really wanted to just make sure I gave you guys another Bayes formula kind of example. What else? I've got one more example, unless there's something you really want to see. Let me show you one more thing. I think this next question is kind of weird. You draw two cards from a deck, from a standard deck. A standard deck of how many cards? Right. Find the probability that the first card that you didn't look at was an ace, given that the second card was an ace. Let's write down some typical things. Let's say A is the first card is an ace, and B is the second card is an ace. And then we're trying to find the probability that the first card was an ace, given, that's the important word here, that the second card was an ace. So it's the probability of A given B. We're trying to find. Okay, so usual deal. I'm always going to do this. Whenever it's conditional probability, I'm going to write probability of the intersection divided by probability of the given thing. Now, the problem here is that the probability of the first card being an ace and the second card being an ace, well, actually, that's not the hard part here. That's not the hard part at all. Because if the first card is an ace and the second card is an ace, well, what's the probability of the first card being an ace? How many aces are there? How many cards are there? So 4 out of 52 or 1 out of 13. And then, given that the first card was an ace, what's the probability that the second card is an ace? Right, 3 out of 51. Or in other words, this top part is just the probability of A multiplied by the probability of B given A. The denominator is a little more interesting. Probability of having the second card being an ace, well, it depends on whether or not the first card is an ace. So you could either have the first card be an ace or the first card not be an ace. The probability of having an ace on the first card, again, is 4 out of 52. Probability of not having an ace is 52 minus 4, which is 48 out of 52. And then the next card can either be an ace or not. We know that the probability of the second card being an ace, if the first card's an ace, is 3 out of 17. The probability of it not being, I don't even know if I need to write this in, but I'm going to write it anyway because, why did I write 3 out of 17? I know why I wrote it really, but like I wrote it, it's wrong. And that's wrong, by the way. It's very wrong. 3 out of how many? 51. I kind of half reduced the fraction, but didn't actually reduce the top part. 3 out of 51, which does reduce to 1 out of 17. The complement here would be 48 out of 51. Similarly, down here, if the first card is not an ace, the probability of the second card being an ace is 4 out of 51. And not being an ace is 47 out of 51. So I'm trying to find the probability of B. Well, it's going to be A then B. So 4 out of 52 times 3 out of 51 plus not A then B. 48 out of 52 times 4 out of 51. Which is really just the usual denominator of Bayes' formula. It's P of A times P of B given A plus P of A complement times P of B given A complement. So we could simplify this, I guess. Feels not super necessary, but let's do it anyway. Actually, it does simplify kind of really interesting. So I'm going to reduce these fractions a bit. 4 out of 52 is 1 over 13. 3 out of 51 is 1 out of 17. And check out my denominator here. 4 out of 52 is 1 out of 13. 3 out of 51 is 1 out of 17. 48 out of 52 is 12 out of 13. 4 out of 51 is 4 out of 51. I feel like this is it's looking interesting here. Nothing's right now. We're good. That all looks good. And then something happens here that I'm forgetting about. Yeah. Oh, I know what it is. I shouldn't reduce this one. So this is going to be, let's factor out the 1 over 13s. We're left with 1 out of 17 on top. On the bottom, we're left with, I'm going to rewrite this as 3 out of 51 plus 12 times 4 over 51. And look at that. 3 plus 48 is 51 over 51. This is exactly equal to 1. So this ends up being 1 out of 17. Kind of weird. Really kind of weird, actually. Or in other words, 3 out of 51. So the probability that the second card is an ace, yeah. Probability that the second card was an ace is 3 out of 51. Oh, no, I'm saying the wrong thing. Makes more sense if I say it the right way. What we actually find? The probability that the first card was an ace given the second card was an ace. Which kind of makes sense if you think about it. So if we ask the question the reverse way, if I said, I know the first card's an ace, what's probably the second card's an ace? You'd be like, well, there's 3 aces left out of 51 cards. 3 out of 51, which is 1 out of 17. It actually doesn't matter that we've interchanged the order. It's just kind of weird here, right? You're saying, I know what the second card was. What's probably the first card was an ace. Well, it doesn't really matter that I showed you the second one first was the first one first. Kind of weird, but makes sense in some strange way.
Does it matter if it's A interchange B over
So A intersect B.
A intersect B over probability of A?
Yes. So the order you write the intersection doesn't matter, but the thing in the denominator definitely matters. So whatever is given is what should be in the denominator. Absolutely.
Why?
Because when you're finding a conditional probability, you're essentially saying the probability of A given B means what is the likelihood of A happening given that B has already happened. It's kind of like saying if I roll 2 dice, what's the probability of rolling a total of, I don't know, 6 given that, trying not to make this too silly here. Given that the total is even. Okay. So there's kind of a lot to say here, but let's do it both ways. So when you're rolling 2 dice, sorry, probably rolling a total of 6 with 2 dice. So when you roll 2 dice, there's 36 possible outcomes. So, right, you can have a 1 and a 1, a 1 and a 2, a 1 and a 3, etc. I don't want to write out the whole table right now because we only got 4 minutes left. But what we're saying here is, what's the probability of rolling a total of a 6? Well, a total of a 6 would be, sorry, brain here, a 1 and a 5, or a 2 and a 4, or a 3 and a 3, or a 4 and a 2, or a 5 and a 1. Those are the ways you can roll a total of a 6. So one way to calculate the probability that the total is equal to 6 is given, sorry, apologies. Probably the total is 6 given that the sum is even is to say, well, it's the probability of getting a 6 and the sum being even, which have to overlap, divided by the probability of the sum being even. It wouldn't make sense to divide by the probability of getting a 6 because then it'd just be 100%. Here, getting a 6, there's 1, 2, 3, 4, 5 out of 36 ways of doing that. Divided by the probability the sum is even, well, what's the likelihood of rolling an even number if you roll 2 dice? 1/2. And that's actually true for any number of dice. If you roll 7 dice, the probability that the sum is even is the same as the probability the sum is odd, which is 1/2. Bless you. Or you could say, I'm going to limit myself to the situations where the sum is even in the first place. So by the way, this reduces down to 10 out of 36, which is just 5 out of 18. But if we look at just the even ones, there's only 18 of them, and of those 18 even ones, 5 of them are 6. So we can look at this reduced sample space and get the same idea, but it definitely has to be the given thing that you're saying. That's our new kind of sample space. So that's what we're dividing by. So, or you can say, oh yeah, 5 out of 18 even sums. Same probabilities over here. So that's how we're divided by that. All right, it'd be fruitless to start another example. So I'll be around. I told you what my office hours are. Usual office hours today and tomorrow. Starting Friday, I'll be in the library from I forget what I said. I think it'll be like 10 to noon and 1 to 3 or something like that. So, but it's on Canvas. Or is it on Canvas? It might not be on Canvas actually. It's now I actually don't. I will post it on Canvas if it haven't already.
So this is a given probability.
A conditional probability.
But what if it's like a factor given?
What do you mean?
Like, I guess like it has to be that.
Yeah. If you're saying this thing is given, we're assuming this thing has happened, and then asking what's the probability that this other thing is going to happen, assuming the first thing has already happened. We are making the assumption the first thing has happened, or this is the given thing, which is actually the second thing in the probability notation. What's up?
Hey, do you have an extra practice?
I don't. I know. I handed them all out. I'm certainly if you.
Can I?
Yeah, you can certainly grab any extras. Yes. Yeah. Totally. Yeah. Go for it.
Thank you.
Of course, you're very welcome. Yeah.
I do for the whole year.
I've enjoyed having you.
Thank you. I'll maybe see you.
All right. Sounds good. Oh, and I should, and oops. What's up?
Something about the 5 out of 36.
Sure. So the 5 was the number of ways that the dice could add to 6. Either rolling a 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2, and a 5 and a 1. Because we're the two dice, pretend like one die is blue, one die is red, right? A red 5 and a blue 1 is different than a blue 5 and a red 1.
Yeah.
There's 5 ways of rolling a 6. And if you write out the whole chart, it's really easy to see like these diagonal lines where the sums are all the same.
Order is there 17 for the DOS parts?
In fall quarter? That's a good question. I don't know. I will take let's see. Let me, I did know the answer to that question a minute ago. Let me end this here real quick though. Yeah. They're probably